For centuries, the scientific consensus on how our universe worked was effectively settled. People believed the cosmos was static and unchanging. That is, until the early 20th century, when an astronomer working at the Mount Wilson Observatory in Southern California decided to test that assumption. That astronomer was Edwin Hubble. He aimed his massive telescope at the night sky and completely dismantled the idea of a stationary universe. Hubble observed that the random, glowing clouds of gas scattered across the sky were actually distant galaxies. More importantly, he noticed they were moving. The space between them was stretching out, proving that the universe is actively expanding in all directions. This observation led physicists to a harsh logical deduction. If the universe is constantly expanding outward, then hitting the rewind button on time means everything must move backward. The galaxies shrink closer together until all matter and energy condense into a single, tightly compressed point. Scientists named this theoretical starting line the cosmic singularity, a state where the entire universe was compressed into an incredibly small, infinitely dense, and intensely hot ball. Eventually, the internal pressure became too immense, causing it to violently burst outward and create the space, time, and matter we observe today. This sequence of events became the foundation of the Big Bang Theory. It provided a mathematical framework for how our universe grew from a tiny point into an expansive cosmos. Yet, in solving the mechanics of expansion, physicists accidentally walked into a massive logical trap. They gave reality a hard start date. The paradox lies in the concept of a starting point. If the universe explicitly began at the moment of the Big Bang, that heavily implies that absolutely nothing existed before it. But nothingness is a brick wall. The idea requires a state where neither space nor time existed, yet somehow produced an explosion of matter. Attempting to calculate a time before time existed completely shatters the laws of physics. To figure out what actually ignited the Big Bang, scientists have realized they have to leave the comforts of classical physics behind and start embracing some radical new theories. The Big Bang has transitioned from a final conclusion into a starting point for deeper questions. Physicists now treat it as a calculation containing literal holes, errors in the math that require a more robust explanation to fix. One of the first major physicists to confront these holes was Alan Guth. He pointed out a glaring inconsistency in the accepted model, known as the smoothness problem. Look at this animation of a standard explosion. If you burst a balloon filled with paint, the resulting blast sends spots flying outward into a purely chaotic, completely random distribution of matter. But as the diagram shifts into this perfectly symmetrical circle, you see the reality of our early universe. Measurements of early cosmic radiation show that matter wasn't scattered randomly at all. It was distributed with evenness and proportion in all directions. To explain how an explosion could produce such symmetry, Guth introduced a concept called cosmic inflation. The mechanics of inflation suggest a mysterious, highly repulsive force acted on the universe a fraction of a second before the Big Bang actually peaked. This force instantly accelerated the expansion, stretching and smoothing out space so fast that matter was evenly distributed before the explosion could create chaos. Inflation successfully solves the distribution problem, making the math work. Yet it still relies on the idea of a sudden explosion appearing out of thin air. The ultimate mystery of where that initial singularity came from remains entirely unsolved. German physicist Martin Boyewald rejects the idea of spontaneous creation entirely. In his view, a cosmic singularity appearing out of absolute nowhere is logical nonsense. In physics, everything has to come from somewhere. To correct this nonsense, Boyewald relies on a complex theoretical framework called quantum time. This diagram illustrates our standard perception of time. We experience it as a smooth, continuous wave that flows endlessly forward without any interruptions or breaks. But look at what happens when we apply quantum mechanics. Quantum time doesn't flow smoothly. It breaks into tiny, distinct segments with short pauses. In this model, the absolute end of one segment acts directly as the spark that begins the next. Apply this logic to the scale of the universe, and a new origin story emerges. Our cosmos didn't start from an empty void. It formed from the severe contraction of a previous dying universe that collapsed in on itself until it reached maximum density. Under this theory, our Big Bang was actually a bounce. When the previous universe couldn't shrink any further, it rebounded outward, meaning our reality is just one phase in an endless, looping cycle of universal rebirths. Even if we accept that the universe inflated perfectly, or that it bounced from a previous collapse, one glaring flaw still stares physicists in the face. What provided the immense, unimaginable energy required to trigger the bang in the first place? Physicists Neil Turok and Paul Steinhardt tackled this question. They realized that the energy source to ignite a universe simply cannot be found within our current boundaries of reality. To explain the trigger, they turned to a radical concept derived from quantum mechanics called brane theory. This animation represents the core of their idea. According to brane theory, our entire three-dimensional universe is actually situated on a flat, elastic membrane, or brane for short, suspended in a vast 11-dimensional space. And we are not alone in the void. A parallel universe sits right next to ours, separated by a microscopic gap of space that contains the fourth dimension. We can't see or touch this neighbor, but it is always there, hovering just a fraction of an inch away. Over vast stretches of time, these parallel branes slowly drift closer and closer together. Eventually, they collide. The sheer kinetic force of these entire realities slamming into each other generates a colossal, blinding wave of energy. In this framework, the Big Bang represents the violent spark created when two parallel realities crash into each other in the dark, rather than a spontaneous birth from an empty void. Pulling back from the math, it's easy to see why describing our universe as a piece of elastic fabric crashing into invisible parallel dimensions sounds like absolute absurdity. Many in the scientific community actively resist these ideas. Scientists are human, and humans are inherently uncomfortable with the unknown. Questioning the accepted, stable dogma of the standard Big Bang model is genuinely terrifying. Yet, despite the initial mockery, these multidimensional theories refuse to die. The incredibly complex mathematics of string theory and quantum mechanics consistently demonstrate that these cyclic and parallel models are entirely viable ways for physics to function. Scientific progress relies entirely on our willingness to push past the fear of the unknown. Just as humanity once had to accept the frightening reality that the Earth was a sphere drifting in space, we now have to confront the limits of our cosmic origin story. Today, cosmic inflation, the cyclic bounce, and brane theory all stand as mathematically possible, equally valid models for how our reality functions. Together, these theories rewrite history. They position the Big Bang as a checkpoint on a much longer timeline, rather than the definitive first chapter of existence. Our entire universe, with its billions of galaxies and countless stars, functions as a single heartbeat in an infinite, rhythmic cosmic cycle. We may never find definitive proof of what existed before time began, but the relentless search for that answer will expand the boundaries of the human mind.